This is the third part of my lessons on bonds. There'll be more lessons on other financial topics after this, including capital budgeting, stocks, and derivatives. So in this lecture, I'm going to talk about correction if a bond is not purchased on a coupon date, and computing the yield given the bond price. And then I have some exercises at the end. The exercises apply to all three of the bond lessons. Previously, we assumed that bonds were either sold at the time of the initial issue or at a time just after the coupon payout, was the payout going to the bond seller, and then the future payouts going to the bond holder, the new purchaser of the bond. But that's not practical. And I have a picture here of what could happen. It's quite likely. So you have your initial issuance of the bond here, time zero, and then someone might sell it. For example, a bank might buy a whole bunch of treasury bonds from the U.S. government and then sell them over a course of time. So let's say it's 6 months in and they sell the bond to a customer, or it could be between two coupon payments. So we need to look at that case. How much should the bond be charged for in that intermediate time there? Just to give you an example, let's say the bank buys several $100,000 treasury bonds, and they're for 10 years, and the coupon payments are twice a year, and so they sell one 3 months in after they first purchased it, and it's at 4% annual, so 2% would be paid out at the semi-annually, which was $2,000. So if they're selling it here, what happens? What happens with this $2,000? Probably the bank wants to keep $1,000 worth of that, roughly, and the user would hope to get this full payment here, but was the bank taking out that $1,000 up front from the $2,000? So we need to figure out some way of determining what this price should be, whether it's after the first initial sale or in between any of these other periods up until the end. So that's what I want to look at here, and in this paragraph, I just mentioned what some of these things are, but I think I explained it already. This is the purchase price. This is the price at some point after, but not just after a coupon payment. A is the coupon payment, and N is the number of periods. And then at the end, you get the last coupon payment. And then you also get the face value, typically the redemption value of the bond at that time. So here we have the formula for the price of a bond, and that's what we've been using all along. What I want to emphasize here, that applies at the initial bond issue date or at a coupon payment date. So like one of these dashes along here. But what's more common is that the settlement, when the bond is resold, is between these periods. And so you have an issue because, say, the bank, let's say it's sold here, and the bank owns the bond during this period here. So they sell it, and then the new bondholder is going to get this coupon. This coupon spans that whole period. So the bank is going to expect to get whatever this amount of interest accrued during this period here. And so you need a way of computing that. And one way is to use simple interest. It's this formula here. So you take P and then the fraction of the coupon period that's transpired, and that'll give you the what's called the dirty price. Another way is to use a compounding formula. It's similar, except you have 1 plus y raised to the k power where K is the fraction of the interval that's transpired. And these are both called the dirty price. The second one is more common. The other complication is the way of computing K varies depending on the type of bond or who's issuing it. And that dates back to before there were computers and people took little shortcuts to do the calculations by hand, or that's kind of what I read on the topic. So the most simple one is this actual option. You just take the actual length of the coupon period, and then you divide that into the how many days. It's basically in days. How many days have transpired, and that would be the most natural. And I assume if computers existed when bonds were first sold, that's all would be used. But they have these other shortcuts, like this one here. It assumes there's 360 days in a year and 30 days in every month, and they make use of that to do the calculation. So I guess if you were like 5 days in 3 months, you would just take whatever those months were. You would just take 90 and 5, and you would get 95, and you would divide by 360, and then you would have to use annual yield here in your either one of these two formulas. Okay, so I'll show you the different options for how the K is computed on the next slide. And unfortunately, these options have persisted, and so you need to know what type of bond you have if you want to do the calculation for the dirty price, and you need to know specifically what type of basis that bond is using to calculate K. Okay, so let's look at the options on the next slide. So this is from Microsoft Excel. This basis parameter is used in the yield function that Excel has and the price function, which actually computes the dirty price. So actual is one of the options, and that's used for U.S. Treasury bonds. Then there's this 30/60, which I mentioned. That's used for U.S. corporate bonds still today, from what I understand. I got this information, by the way, from ChatGPT, although this here is from Microsoft Excel. The explanations are from ChatGPT. Then you have actual, then 360, then actual 365. This is getting closer to actual. Then there's the European 360. It's similar to this one here, but there's different month rules. And I'm not going to go into the details here. I just want to make you aware that these options are here. And on the next slide, I'll show you the Microsoft Excel price function, what the input parameters are. This is the price function from Microsoft Excel. I actually got this page from Microsoft, and what's showing here are the different parameters you need in order to use this function, which will give you the dirty price. So you need the settlement. That's when the bond was purchased, the actual date, or repurchased, and then the maturity, when the bond is redeemable for the redemption value. Then there's the rate, the coupon rate. Then there's the yield, which doesn't have to be the same as the rate. Security's annual yield. The redemption, that's based on $100 face value. You remember we did this before in one of the examples. We had to divide out, so we just get per $100 face value. The frequency, so that's how frequently the coupon payments are made. So typical is annual, semi-annual, monthly, quarterly. So they have different options here. In fact, there isn't even a monthly option. There's just annual, semi-annual, and quarterly. Apparently that's the only ones that are used. And then the basis is what I was just talking about, which I showed you on the last slide. And there were the values between 0 and 4, which the most common sense one is actual, but unfortunately, as I mentioned, some of these other ones are still persisting. So you need to be aware of that. If you're doing a calculation for a specific bond, you need to know which one of those basis options are being used. As an example, consider a 30-year U.S. Treasury bond with an annual yield of 1.61%, an annual coupon of 1.25%, interest paid semi-annually, and a redemption value of $10,000, which also equals the face value. We've been assuming that pretty much throughout. The bond was purchased by a brokerage house. At what price should the bond be sold to achieve the advertised yield if the settlement date is 5 June 2020, when the bond is resold to a customer, and the maturity date is 15 May 2050. So the bond was sold a little bit after the initial issuance, so that makes this an example where we need to compute the dirty price as well as the clean price. So for this worked example, we assume semi-annual coupon dates of May 15th and November 15th. So we're just working back from the maturity date here, assuming that's one of the two coupon dates, and then just going forward 6 months, that would give us the other coupon date. We take K to be the fraction of the current coupon period elapsed from May 15th, this would be in 2020, to June 5th, the settlement date, and that's 21 days. And this period, May 15th to November 15th, is actually 184 days. So our fraction K would be 21 over 184, or approximately this decimal here. So we have the other variables. The yield rate is half per half year. It's this number here. Just divided our 1.61, made it a decimal, and then divided by 2. Total number of payments is 60. No payments were missed. The broker sold the bond before any coupon payments. Redemption value, which equals the face value, is $10,000. The coupon rate per half year, we just divide by 2. We get this here. The coupon payment is this amount. So if we use the bond price formula that we've been mentioning before, we get this price here. And that would be the price of the bond at the issuance in order to produce this particular yield, 1.61. And we want to get the dirty price because that's what we want to know exactly what it's being sold at for to the customer. So there's two ways, as we mentioned before. One is to use the simple interest formula, that was K, plugged in, and we get this number here. And if we use the alternate formula, this compounding formula, we get a slightly different number. And then I just made a note here as a second example. If the bond was sold later, say the 10th of November, so just before the first coupon, K would almost be 1 at that point. And then our dirty price, using the same procedure here, it would be a bit more, 92.1775. That's because the brokerage house wants to recoup most of the first coupon, right? Because they've held it almost the entire period. And then if we use the alternate formula, we would get this number here. On the next slide, I'll compare what I got here using our approach to what you get using the price function from Microsoft Excel. Let's compare our result to what you get from using Microsoft Excel. I copied our results from the previous slide. These are per $100 of face value, so I needed to divide each of the results by 100. If we put the information into the price function of Microsoft Excel, we first put in the date, settlement date, using the date function, then the date of the redemption, which is in the year 2050. Then we put in the coupon rate, the yield, the cost, or the face value, I should say, per $100. So our face value was 10,000, but we needed to divide by 100, so we get 100. 2 is the indicates semi-annual coupons, and 1 indicates that we're using the actual to actual computation for the value of the K. So everything's been converted to $100 per face value. The value P that we got here, just copied it down here again, was from the bond price formula, is the value of the bond as of the previous coupon date, May 15th, 2020, accumulating this forward to the settlement date using the alternate formula. In other words, this formula up here, we get 91.5449. The market clean price is then found by subtracting accrued coupon interest. So we take 21 over 184. Again, we normalize this per $100 of face value. We get this number here. Then we subtract that from this number here, and lo and behold, we get $91.4736. So apparently that's how Excel does the computation. It computes the price back to the previous coupon. It uses this formula, the alternate dirty price formula, and then it subtracts the accumulated coupon interest to get the clean price, and that's what it gives you. Okay, so just beware if you're using Excel, this is what you get. And the other thing is they also have an accrue function that I looked into in Excel, but the way you have to populate it is very non-intuitive, and I would just recommend doing it manually like I have here. But just to make you aware, there's also an accrue function that does compute this, but again you need the way you have to populate it is very non-intuitive. Before I get to the definition of the clean price of a bond, I wanted to analyze the dirty price a little bit more. This is the same example we've been working on, and I'm showing the first 4 periods out of the total of 60 periods for the Treasury bond. And then I broke it up arbitrarily into 8 pieces. I could have done 4 or some other number, but I decided to just take the 8 intervals along the coupon period and then compute the dirty values. So this is actually a dirty value, bond value chart. So if you look at the first period, this is how much the bond would sell for after this fraction of 184 days. So 23, then 46, 69, and so forth. And so you see here that the price goes up as you move along because the coupon is effectively accumulating interest, and whoever's selling that, for example, a brokerage firm or a bank, they want to recoup that. So the closer you get to the end of the first period, this number is going to go up to almost the price of the initial price plus the first coupon. And then when you go to next period and you compute the dirty bond price, the difference, which I'm showing here, so this is the difference between, for example, this number and this number, is the coupon. There's a slight rounding here. It should really be 62.50 each time, but I had some rounding errors. And the same thing here. The price, the dirty price goes up and up because over this first, between the first and second period, the second coupon is accumulating interest, and whoever's selling it wants to recoup that when they sell the bond all the way up to the end. And then you have this drop again between this number here that I'm pointing to and this number here. It's 62.50. Okay, so that's the idea. You're as a seller of the bond, you're expecting to recoup whatever interest is accrued to the coupon during this interval. Now these intervals are half-year intervals, and again, I'm just showing 4 out of the 60 periods in the life of the particular Treasury bond. And I did this using Microsoft Excel. I actually did 2 sheets. I have one sheet that has the dirty prices, and then a little bit later on I'll show you a second sheet from the spreadsheet that has the clean prices, and you'll see the difference. And I'll make that available to you. I'll tell you where that is. It'll be on the same directory as the program I was just talking about. On the next slide, I'm actually going to graph these, and that'll give you a little bit more insight also. So here we have a graph, also done using Excel, of the points on the table from the previous slide. This is from here to here is the first row. It's just showing how the dirty prices go up, roughly 62.50. Then this line here is really an artifact of the drawing tool in Excel. There might be some way of eliminating it, but it should not be here. Basically, when you get right before the end of the first period, there's a drop off. There's no line. It just drops down to this number, and then you have this going again. And then there's another drop off, and the line's going off. So again, this line, this line, this line, this line, and so forth. Those should not be there. They're just a drawing artifact. Okay, so tracking the dirty price, you get this strange zigzag graph that we are showing here. And then the fact that this drops off at each point by the amount of the coupon, we can prove that. It's a bit ugly looking, but I have the calculations on the next slide just to make the point even further. So here's the calculation. It looks pretty ugly, but it's not so bad. The fact that the dirty price drops by exactly 8 at the end of a period can be proven as follows. Noting that K, our fraction, is 1 just before the end of the coupon period and 0 just after. So we take the dirty price of a bond just before the end of period with M remaining coupons. And that's this here. This is the adjustment for the dirty price, and noting that K is 1. And then we subtract from it the dirty price of the bond at the beginning of the next period, at which there are M minus 1 coupon payments remaining. And in that case, K is 0. So we have this thing on the right. And then we multiply through 1 plus Y times the terms here, and we get this. And then here we just have a minus 1 times all this. So we get that. Let me use the crossing out. So this and this cross out. And then you can take this Y here and A and Y, and you get this term here. And then let me go back to pointing again. Then what's left on this side here is the A times 1 minus this over y. And on this side I didn't touch anything at all. That's just the same as this term here. Go back to crossing out. So this cancels that. And all you have left is the ay divided by y, and you get a. So continuing with our thought here, the reason for the increase in the price over a period is that the dirty price reflects the accrued interest on the coupon before it is paid out at the end of the period. Look at it this way. If the price did not reflect the accrued interest on the coupon, everyone would buy bonds just before the coupon dates and immediately get the coupon payment for the previous period. So clearly the institutions, banks, and investment firms, they're not going to let that happen. So that's why the dirty price is used as the sale price. The dirty price or full price is the total cash you pay at settlement. It equals the clean price plus accrued interest earned by the seller since the last coupon date, as we saw in our previous slides. Economically, the dirty price is the value of the bond's remaining cash flow as of settlement, which lines up with paying clean price plus accrued interest. Equivalently, the clean price, also called the flat price, is the dirty price with the accrued interest stripped out. So clean equals dirty minus accrued interest. In many markets, especially the U.S., bonds are quoted at the clean price, so the quoted figure does not jump on coupon dates. You add accrued interest to that quote to get the actual purchase amount. So in summary, the bonds are typically advertised at clean prices and settled at dirty prices. And just what I've said here in words, I wrote down in equations here. In terms of equations, we have the following. The accrued interest, I sub k, is just the k times a. K is days accrued during the coupon period, and then the total length of a coupon period times a. So it's pretty simple. Then the clean price is just the dirty price minus this amount of accrued interest, or equivalently, the dirty price is the clean price plus the k times a. I have some example and a diagram on the following slide, so let's have a look at that. So this is the same example we've been looking at, and in fact I took the same 5 periods and the same increments along the way, and instead of the dirty price, which we saw before, I computed the clean price and I put that in these rows here. And then when you graph it, you actually get, it should be exactly a straight line, but there's a little bit of rounding off here. So you essentially get a straight line. And this, again, as I said on the last slide, this is what's advertised. You'll see this, if you want to buy a bond here, you'll see this clean price advertised. And then what you actually pay is the dirty price. So let's change the topic a little bit here and talk about yields. It's possible to determine the yield when given the bond price, the coupon rate, and the term of the bond. However, there's no closed form for the yield given this information. You need to use a numerical approximation method. Microsoft Excel has a yield function that will give you a very good approximation given these inputs here. Let's just go through it quickly. The settlement date, that's when you bought it. The maturity, when the bond is redeemed. The coupon rate per year. Then the purchase and redemption per $100 of face value. That's just how bonds are quoted, so that's why they request the information in that format. Then the frequency, so there's either annual, and you would put in a 1 in that case. Semi-annual, you would put in a 2, and then quarterly, you would put in 4. And those are the only options. So apparently bonds are only have coupons at these options here, or at least in terms of Excel, that's all they're going to give you. And then there's the basis. If you recall from the price function that we talked about earlier, it's the same thing where you have these different shortcuts like 30, 360 that we talked about, or actual. So you need that information, and then you get back the yield if you put in all this. So let's look at an example in the next slide. Consider the example from the previous lesson where we had a Mr. Everest. And if you recall, we computed the price of a bond that he purchased. It was this number here. But let's now say that we're given the price and we're asked to find the yield. In order to use the Excel yield function, we need the actual dates when the bond was purchased and when it was redeemed. And we were told in the example was 5 years. So we'll just pick two dates. I use January 1st, 2000 and January 1st, 2005 as the maturity date. And we were told in the example the coupon was 4%. Then we need to compute the purchase price as a percentage of the face value. So this number here, this purchase price, if you want to get what percentage it is of 50,000, you multiply by 100 over 50,000. So it's 95.62396% of the face value. And then the redemption value is 100% of the face value. There's no difference between, in this case, and that's typical. There's no difference between the redemption value and the face value. The frequency is 2, and I didn't use the basis. I allowed Excel to just default. And so you see the input here. You notice the dates, we had to use a function to get the date in the format that the yield function was expecting. It's pretty easy once you know what to put in here. So it's date is the year, month, and day. And then the year, month, and day for the redemption. Coupon rate, the number we just computed here, the purchase price as a percentage of the face value. The redemption value was a percentage of the face value. It's 100. And then 2 was for the biannual. And we get this number here. So it was pretty close. The initial example was 5%. So when we had to approximate it here, we just came off by a little bit. And I just have a note here, which I mentioned on the previous slide, that there's no closed form for y given this other information. You need to use a computational method, and that's what's being used in Excel and also in various Python programs that also use these procedures to find the solution. On this slide and the next couple of slides, I have some exercises. One caution, these pertain not just to this lesson, but the previous 2 lessons on bonds. So the first one is compute the price of a 10-year zero coupon bond that effectively yields 3.5% per year under the assumption of yearly compounding. So we want to find the price here. The redemption value of the bond is $15,000. And I'll give you the answer. We use the bond price formula here, but A is 0 since there's no coupon. It's a zero coupon bond, so this drops out. And B is 15,000, so we just plug those in, and we get 10,633.78. If no compounding is assumed, we need to compute the present value of $15,000 under the assumption of simple interest. And in that case, we have the price, 15,001 plus 10, it's 10 years, times the 0.035, and we get this answer here. The second problem, compute the price of a 5-year bond with semi-annual coupon payments at a nominal annual rate of 5%. The redemption and face value are the same. We've been typically assuming that, and it's $50,000. So the nominal annual yield rate is 4%. Hence, use the balloon loan calculator, which I've made available previously, and I'll be putting the link to all the different calculators in the information to this video. And the coupon is half of this, right? It's half of this percent, because it's semi-annual, times the 50,000. So the coupon is $12.50, and you plug all this information into the balloon loan calculator, and you get this solution here. And then this is just a question: is the bond from exercise 2 purchased at a premium, a discount, or at par? The coupon rate is higher than the yield, right? The coupon rate and the yield is, and so from our previous analysis, that means it was purchased at a premium. I guess we could have also looked at the purchase price, right? That's bigger than the face value, so that would also tell us that the bond was purchased at a premium. I have a few more exercises on this slide. Using the information from exercise 2 on the previous slide, create a table that shows the bond price for the following nominal annual yields, assuming semi-annual compounding, so 2, 3, 4, all the way up to 8%. Don't forget to convert the nominal annual yields to semi-annual yields. Also keep in mind that the coupon is the same for all cases in this exercise. Okay, and I actually gave you the answer down here. So this is where the yield and the coupon rate are the same, so you would get the 50,000. This is where the yield is less, and the bond price is more, and here's where the yield is more, the bond price is less. Then I noted here whether you're buying at a premium or a discount or at par. Then the fifth exercise, also going back to exercise 2, create bond schedules for 2 cases when the yield is 3% and 7%. So this was the calculator I talked about previously, the bond schedule calculator, and I'll make that available. I'll give you the link. It's a program on GitHub. I know I mentioned it in a previous lesson, but I'll give you the link to all the different programs. All right, I have a few more exercises on the next slide, and then that'll be it for this lesson. We have 3 more exercises. The first one is compute the dirty price for a 20-year Treasury bond that is to have an annual yield of 1%, compounded semi-annually, an annual coupon rate of 1.25%, interest paid semi-annual also, and redemption value is the same as the face value, and it's in the amount of $25,000. The settlement purchase date is 15 June 2020, and the redemption date is 31 August 2030. Okay, so I have a hint, essentially the answer here. If you want to give it a try, you may want to pause here, otherwise I'll read through it in a second. Okay, so the first thing you should notice is this is a resale, because this is a 20-year Treasury, and between settlement and maturity there's only 10 years, so this is a resale. Then the other issue we have is we're given the maturity date, but we're not told when the bond was first issued or when the coupon dates are. So I worked backwards 150 82 days to August 31st. And I used that. Again, if you're using some type of online calculator, they may do something slightly different, but that's what I did here. So there are 21 coupon payments remaining, n equals 21. Use the balloon calculator, and I'll give you a link to all the different calculators and the information to this video. Use that calculator to compute the price of the bond at the time of the last coupon payment before settlement, and we get this number here. And then we use this as P in our two different formulas for the dirty price. I also used an online site, this link here, to count the number of days from March 31st to the 15th of June. So I went from the last coupon date to the settlement date, 15 June. And I counted the number of days, or at least this calculator did. So it was 105. And then, as I mentioned, there was 182 days in this coupon period. The other coupon period would have 183. And I could use that to compute K. And then I did the two dirty formulas, the simple interest. I got this value, and then I used the compound interest to get this value here. Then exercise number 7, use the simple interest version of the dirty price formula. Show that the clean price can be represented with this formula here, where P, K, Y, I, and B are, as we've been talking about before. It's the price at the time of the last coupon. This K here, the fraction of time that is elapsed from when settlement was done to the previous coupon, the yield, the interest, and B is the redemption at the end. We assume the face value is the redemption value, and so we have A equals I times B. And then you can, from there you can compute the formula. And then the last problem is using exercise 6 again, compute the clean price. We just use this formula here, the dirty price minus the fraction K times A. And I used the simple version of the dirty price, and I got this here. So that's the end of this lesson. It's also the end of the series of 3 lessons on bonds. If you like this, please give it a thumbs up. I do have more lessons on financial math. I'll have some lessons on capital budgeting following this.